I hope all of you are able to see this.
Yes, sir.
Okay, welcome back. Why one has to detect this, what we can call gravitational waves? Scientists have realized that and also relied exclusively on electromagnetic radiation earlier to this, particularly maybe the visual radiation or X-rays, radio waves, gamma rays, or even some kind of a microwaves to study the universe. You might have seen pictures on the universe in visible, universe in X-rays, universe in radio waves, universe in ultraviolet rays, universe in different microwaves of that kind. Means either sun or maybe any of the stars or anything in the universe can be detected by making use of this kind of a radiation. But none of them have tried with the gravitational waves. Some are even trying to use the subatomic particles called neutrinos as well to detect the universe or to detect the processes which are happening in the universe to a great extent. Each of these messengers, these are called the messengers, these are called the one which can communicate to us, communicators they can call actually, or the one who can carry the message and hand over to the others of information, messengers of information, provides the scientist with a different view of the universe, but it is a complementary to the one to each other. Maybe either you can study under visible or maybe X-rays or ultraviolet or maybe under radio waves, different information will be gained. For example, if you hold your hand near to a torch, you may not see what is there in your hand actually. This is what is there is inside. Okay. But if you allow the X-rays to pass through, and after some technique of developing the X-ray film, certainly notice that what's there inside your hand actually. Means like in terms of the bones or shape of the bones or cracking in the bones. That is an indirect way to detect. If not, well for well off. Even for a material, for example, all materials are under exposure to X-rays or maybe some kind of a radiation whenever you go to a metro station or any kind of a sensitive and secure zones. What they will do, instead of without opening your bag, without opening the material, they can sense that what is inside actually. If something is an unusual, unexpected, they can ask you to the show or to remove or keep aside of that kind. Otherwise, everything is allowed for security issues of that kind. Similarly, is without it, without opening means what's there inside the entire bulk material, they can check. Gravitational waves, however, are the fundamentally waves which are unrelated to the electromagnetic radiation. That is the great beauty. Okay, they are as distinct from the light as hearing is from the vision. Assume that light waves means that the electromagnetic waves are the one which can, either you can see from some kind or maybe you can sense through the detector of that kind. But electromagnetic, sorry, gravitational waves, you can't be an electromagnetic radiation of that kind. For example, they are the distinct from the light as your hearing is from the vision. What I can say that actually lightning you can see, but you can't hear that sound. The sound, thunder or storms, like thunder they can call, what you can call gurugu, they can call, that should be through only through the sound intensity. Imagine if we are, if you being a human being, if you were a species that only had eyes to observe and understand the universe, no ears, no detector to listen to the sound. We are having only the eyes to see. Now you are seeing the screen, you are seeing the display, maybe the smaller or larger, doesn't matter. Okay, somewhere some noise is coming, doesn't matter. Okay, if you are only display is there, you can go through the text. No need of me to explain from far away. I can share this through you to the WhatsApp or any kind of a messenger. Okay, where you can read. The same material is also available in textbook. The same material is also available in reference books. Maybe if you find some 10 books, actually it is not a big task for you to go through. Then why we need a teacher to, why we need a teacher actually, why we need a faculty. If faculty or maybe teacher is the one who can explain you what it is there, what the way I read, the way I understand, I can explain to you in a way how much I can convince you in such a way where the thoughts can be convinced for you. Means the sound makes you to convince in such a way that even though the text may not convince you through your naked eyes what you are going to read, the science, in the sense, what my intention is that both audio and video put together makes as the multimedia, multiple medias which can communicate or convey the messages from one person to another person actually. Here, so far the scientists from astronomy or maybe in general to understand the universe of different properties need not be always with the celestial body of that kind actually. Have used the technique of electromagnetic radiation to understand the universe. But if you are having only human eyes actually, then tough task. You can learn a lot simply by studying the light from the objects studied well in the last century. Last century means before 19th century. The day came one day, someone invents something called an ear, which senses distant vibrations in an air or even in water, or vibrations that had been there all along, but you could not detect simply by using your eyes. Means sound waves can't be detected by the human eyes. One can use the ears to a great extent. Consequently, this new detector ear enables you to learn things about your world, that is the universe, that you would never had gathered the information from the electromagnetic light earlier. It has opened a new window, it has opened a new channel, it has opened a new scheme or school in such a way, a thought to understand the universe. That is the gravitational wave. More importantly, since gravitational waves interact very weakly with the matter, in the sense not like an electromagnetic radiation. If see, for example, if you allow the light energy to pass through a material, the energy can be either absorbed or reflected or refracted or even bent by gravity itself. That is the Einstein's theory. Means either absorbed or refracted because you are seeing the display, because the display reflects the light. You are seeing the wall, all objects around you, mainly because of the reflection. If something is refracted, maybe the bending of the light in a media, how we are getting the light radiation, or even absorbed. Because of the absorption, you are getting objects becomes heat, object becomes hotter actually. Means, for example, microwave oven, for example, what you are expecting, they allow the microwave to pass through the material, some stuff where the temperature goes up. Or even microwave ovens are also, you might have heard actually. Microwave technology is another kind. Or microwave radiation is the one which can travel through billions of kilometers without affecting to a great extent. But they travel through the universe, which were virtually unimpeded, carrying the information. Unimpeded means undisturbed, carrying the information about their origin that is free of distortion. This is the beauty. This is the beauty of it. For gravitational waves that were detected are still detected by the LIGO observatory are caused by most profoundly cataclysmic events in the universe. Means they are the one actually. Means they can be observed either by the collision of the two black holes, merging of neutron stars, exploding of the stars, and possibly even the birth of the universe itself. This is the beauty. That is why LIGO has removed a wheel in the sense a doubt actually of misery on the universe, and has helped the scientific community in exciting new research in physics, astronomy, and astrophysics. These are different terminologies actually, where a very thorough understanding is going on across the universe. Wow. I don't know. This is the artistic depiction you might have seen earlier of a neutron star collision after inspiral. Neutron stars are spiraling around each other. If they collide, actually, how it behaves? Looks like it is not in the same case. If the spectrum is taken invisible, it appears like that. Maybe sometimes blue is hotter, white may not be after that kind, or maybe these other colors are having different temperatures, and the light, the temperature, because depending on the temperature, they emit light radiation. You can, of course, either visible or maybe different spectra. Because of the temperature, we can expect that what kind of radiation we can expect around the background too, to a great extent actually. White is the color which is the mixture of the all, which is too much hot to a great extent. Yeah. Sources and types of gravitational waves. I'll go through, it is not much actually. Our intention is to see that how that gravitational waves were detected. Technically speaking, every physical object that accelerates produces the gravitational waves. Assume that if we are moving on a vehicle, two-wheeler, can you expect that the gravitational waves will be produced? No, it should be accelerated at a rate which is very faster actually. Very faster means not at the macro scale, micro level of that kind. This includes the humans, cars, aeroplanes, fine. They generate, no issue, but not to the extent. Okay. But the masses and the accelerations of objects on Earth are far too small to make gravitational waves big enough to detect with our instruments. We can have that. Every movement is an acceleration. Every acceleration can be detected, and that produces the waves. Actually, those waves can be detected or not. It's tough task. To find the big enough gravitational waves, we have to look far outside our own solar system. That is the purpose. That is the purpose. The universe is filled with incredible massive objects. That's why it is an open laboratory undergoing rapid accelerations that generate gravitational waves that we can now detect. We now think it of working in astronomy, working in astrophysics, working with space physics, working with atmospheric physics, either of the Earth or maybe different planets together, working on galaxies, working on the universe. You don't require any experiment to initiate. Universe itself has initiated several experiments. Universe itself has created so many things, fantastic things. Only thing is that we have to observe and observe and observe, and those observations can be interpreted, those observations can be narrated, those observations can be explained by our understanding with the theory, whatever it is available or whatever we have undergone, either in your second year of master's course or in your PhD program, or if for a project in your fourth semester, or maybe any kind of work, whatever you are going to take it up. If you take it up this type of a problems as a challenging problem for you to solve, you will get innumerable number of ideas to a great extent. My intention is that don't expect always from the gravity, always from the astronomy, astro of that kind, enter universes of that kind, starting from a small experiment in your laboratory, starting from a small theory in your laboratory, starting from a small solving a problem from your notebook to by making use of a computer for solving so many iterations. The entire universe is filled with incredible, means in large, huge number of massive objects which are undergoing rapid accelerations. Rapid in the sense they are accelerating not in a systematic way. It's very fast actually, very fast, and they're also changing from time to time that to generate the gravitational waves that we can do. Now, knowing these things, no objects are pair of black holes or neutron stars orbiting each other, a neutron star and a black hole orbiting each other, or gigantic stars blowing themselves up at the end of their lives uses the example. This is a repetition, let it be, it doesn't matter. Astronomers have defined them into four categories of gravitational waves based on what object or system generates the waves. It's only a classification actually, nothing to do with that. Universe will never comes with classifications. Means at least we can say that because of these classifications, how we can understand. For example, it's a continuous generation of the gravitational waves, compact binary inspiral gravity waves, stochastic gravity waves, and a burst of, due to the burst, we can have the gravitational waves. This is the source. From the source, we can call actually. Each category of objects generate a characteristic set of gravitational wave signals. This we will study one after the other. I will not spend much time here. This is the continuous gravitational. What it shows that actually depiction of a super dense and a compact neutron star. Super dense, density wise, high dense, and in terms of the size, it is very compact. Continuous gravitationals are expected to be produced by a single spinning massive object. A massive object is there, like neutron star, it spins on its own. Because of the spinning, it gets accelerated actually, generated and generates the gravitational waves. Any bumps means humps, they can call humps, you can call no? Humps or bumps, or an imperfections in spherical shape of this star will generate gravitational waves as it spins. If the spin rate here of the star stays constant, it moves with constant spin, it emits gravitational waves. Gravitational waves is continuously emitted with the same frequency and the amplitude. That's why these are called continuous gravitational waves. These are emitted because for a star, for a neutron star, it is fixed. One can understand through their properties. If we continuously understand the gravitational waves, we can say that what kind of a star. Second one is that compact binary in spiral gravitational waves. You can see in the image here, these two are there. Binary neutron star, which are spiraling each other. Within that, there's a field. This is not there. This is artistic view actually. There's no doubt. Another class of gravitational waves is compact binary in spiral gravitational waves. So far now, all the objects which were detected by LIGO fall into this category. Compact binary in spiral gravitational waves are produced by orbiting pairs of massive and dense objects like white dwarfs, stars, dwarf stars, black holes, neutron stars. There are three subclasses of this system in this category. Three are binary neutron star, BNS, two neutron stars orbiting each other, or binary black holes, two black holes orbiting each other, neutron star black hole binary, that is NSBHB, a neutron star and a black hole orbiting each other. See, there is a simple way, three combinations, two neutron stars or two binary holes, or maybe one binary star and one neutron hole. To a great extent they can, because of this, each binary pair creates a unique pattern of gravitational waves that depends on, among other things, the masses of each object, how their orbits are oriented with respect to the Earth, and how far they are. But the mechanism of wave generation is the same across all the three. It is called in spiral, spiraling each other. This entire thing was happened in detected in 7.4 millisecond. Remember, this I have not told you earlier. Even though the waves which are coming, it is not for longer duration. The duration is very less, 7.4 millisecond. This is happening. Another category is that is a computer simulation, shows that the collision of the two black holes as observed by the LIGO on 14th September 2015. The black holes in the animation are based on the actual data of the collision. I will show you video first, then you can think it of. Please come. See, it is not something like that you are cooking. Even in some of the huge rivers, this type of phenomenon will happen. See that, my God, two black holes become a single and nothing, and see that what. I'll repeat. Are you able to hear the sound?
No, sir.
1 second.
In the distant reaches of
Now?
the universe, two black holes, each about 30 times as massive as our sun, were locked in.
Now? Or I will share.
Yes, ma'am.
You listen later, doesn't matter. This is a sound also
orbit
you are
and
getting.
spiraling in towards each other. The only visible traces of this spinning cataclysm would have been the way their gravitational fields warped the light of distant stars. Even as they collided and merged, there wasn't a flicker of light to be seen. The real and very violent action in this system was in the form of gravitational waves, ripples in the very fabric of space and time. These waves were constantly draining energy from the black hole orbits, leading to their ultimate collision and merger to form a single black hole. At that instant, the power of the gravitational waves was 50 times greater than that of all the stars in the universe combined.
The gravitational force
That pulse of gravitational waves, lasting only a fraction of a second, expanded through the universe, passing unimpeded through countless galaxies. About 1.3 billion years later, it reached Earth.
Gravitational wave. The waves generated during that coalescence is hardly about 7.4 millisecond. That signal will travel through the space for billions of years. That should be detected. I don't know whether you got it or not. When two things collide, that becomes one. Two becomes one, or maybe many becomes one in a fraction of a second. That fraction of a second, it generates an energy. That energy, generated energy, is in a different form. That will not be the repetitivity. That is not one peak you will get actually. One peak you should not delete actually. One peak or maybe whatever you are getting, either the loss of the signal or maybe the generation of the signal for manifold. They're saying that 50 times more than the strength of the rest of the part actually. If you ignore that, if you are unable to detect that, actually you may not notice the coalescence of any of the two stars.
Waves alternately stretch and squeeze space itself and everything they pass through, but the effect is minuscule. Their effect on Earth here has been vastly exaggerated to help visualize something that is otherwise invisible on this scale.
See.
To detect them and directly measure their
This is the LIGO
properties,
experiment.
scientists built LIGO, the most sensitive measuring device ever made.
One
LIGO
is with
uses a
two
device known
mirrors.
as an
This is the
interferometer
laser
to measure the
experiment.
tiny
This is the detector
displacements in
part.
space.
See, if both are operating
In this
without
simplified
this-
representation, a
without
laser
the
beam is sent towards a
gravity waves,
partially reflecting mirror and split along two paths.
see that.
The beams travel along the 4-kilometer arms and
The
reflect
4
back
kilometer
towards the
distance of
central
separation
mirror,
between them is
which
4
recombines
kilometer.
them, directing their light to a detector. As the gravitational waves
Because
pass,
of that,
the distance between the central beam splitter and the
you
end
get some
mirror
structure.
stretches along one arm
It
and
gets cancelled to
compresses
each other.
along the other.
Because of the gravitational waves,
This changes the time it
this
takes the
changes the
light to
time
travel
between these
along the
two.
arms.
Then either interference or maybe
The
distance
recombined
can
light
go across.
waves shift with respect to one another and produce a signal at the detector. Incredibly tiny stretching and squeezing of space can actually be measured directly in this way. How little does space distort to make this signal? Let's zoom into a hydrogen atom until we reach the proton at its core.
How that
LIGO is
signal
so
strength is very
sensitive it
weak.
can measure changes in distance as tiny as 1,000th the diameter of a proton.
See that.
And this tiny measurement, made by LIGO, was the final step in a journey that began 1.3 billion years ago in the distant universe when two black holes collided.
17 they did, 15 they detected. See that this is the sound. Sorry. Are you able to hear? One confirmation.
Yes, sir.
Are you able to hear the sound which is coming from the video?
Yes, sir.
Oh, good. I will continue. Just a small
3
step.
billion years ago.
Silent. Here, what happens? My thought is that in such a way, you see, this is the you are learning very interesting subjects in landmark experiments. Only 8 experiments are there. This is the last experiment in your curricula. Doesn't matter. You go through later, one after the other. After preparing for the examinations, you can spend time to understand the physics part of it. In spiral occurs over millions of years as space of dense compact objects which are revolve around each other. Or as they orbit one to each other, they radiate gravitational waves that carry away some of the system's orbital energy. Over millions of years, this causes the objects to move closer and closer. Because they carry the sum of the orbital energy outward. That is why they lost the energy. That's why they are moving. They closer they come, the faster they orbit each other, which causes them to radiate stronger the gravitational waves, which causes them to lose more orbital energy. In such cases, even come very closer, orbit very faster, lose more energy, moves very closer, again orbit faster. This process can go up and until they merge. Finally, the objects are doomed, inescapably locked in a runaway, accelerating spiraling and embrace and creating the simulations. Because of that, this accelerating spin, because they're rotating themselves, accelerating spin process is analogous or similar to that of a spinning of a figure skater, they can call. For a skater, they are comparing. Imagine that skaters outstretch their fist, or the neutron stars are black holes, and skater's body is the force of gravity binding them together. Unless you know how that scatters, it is difficult for me to convince you. I will show you a video for that. As the spinning skater pulls their fist in towards their body, that is, as the objects orbit closer and closer, they spin faster and faster. This is the according to the conservation of angular momentum in action. Unlike a scatter, for example, however, pairs of neutrons or maybe black holes cannot halt their rotation. The process of emitting gravitational waves and orbiting closer and closer sets off an unstoppable sequence of events that can only end with the two objects. Therefore, the nature or the universe, they can call nature of a binary inspiraling system, means that the waves radiated by the system change over time, slowly increasing the frequency of in frequency as the objects move closer together. At some point, the pair will be orbiting each other at the rate that can finally detect, and radiating gravitational waves will enter our sensitivity range. It turns out that by the time this happens, the objects are just seconds away from colliding. So one catches the last few orbits before the pair of collides. That should be captured. Consequently, the time they spend orbiting and emitting the gravitational waves in a detectable range is very brief, ranging from fraction of a second to the tenths of a second. There are two clippings here. Just watch. See, same thing I have shown. Another one. Right before binary neutron star merges. See the peak. See that line. Go up. Sorry, I'll play for you once again. My God, it has gone somewhere else. Huh? These are continuous gravitational waves. This is the pulsar. This is the bump. See that bump here? Ripples in the space-time, we just see that. They are emitted in all directions. These waves are very weak, but are always emitted. Gravitations will reach us, the Earth, even from the beam, never points towards the Earth also. See that. From rapidly rotating neutron stars in our galaxy. See that here. This is the Milky Way galaxy. Okay. Being this, yeah, here what happens, the masses of the objects involved dictate how long they emit, and detectable gravitational waves, which were detected by the laboratories, any of the laboratories. Heavy objects like black holes, or if they move through their final inspiral one, rapidly lighter objects like neutron stars. This means that black hole merger signals are much shorter in duration than neutron star merger. This is only for comparison. For example, the first pair of merging black holes, which was detected by LIGO for a 2/10 of a second long, 2/10 of a 2 by 10 seconds of a long, 0.5 seconds, point not, yeah, 0.2 seconds of that kind. First neutron star merger LIGO detected on this signal on in August 2017, which generated a signal over 100 seconds long. This is the experiment what I showed, the bump. The same case. The two examples of the actual gravitational waves illustrate how different systems of merging objects display unique signatures in their interferometers. Shorter signals means more massive objects like black holes, which were involved. Otherwise, longer signals show that they are lower mass like neutron stars. Because of that, three great scientists got the Nobel Prize for the discovery of the experimental discovery of the gravitational waves. For decisive contributions to the LIGO detector and the observations of gravitational waves, where Einstein gave theory in 2000, sorry, 1915 or 16 of that kind, 1916, about 100 years. Rainer Weiss, then Barry, C. Barish, and Kip Thorne. What they mean? On September 2015, the universe of gravitational waves were detected and observed, which was about 1.3 million years away from them. The signal was very weak. Gravitational waves spread at the speed of the light, filling the universe, as Albert Einstein described in his theory of general theory of relativity. They are always created when a mass accelerates, like when an ice skater, ferrites, or pair of black holes rotate around each other. Einstein was convinced it would never be possible to measure them at that time. But the LIGO project achievement was using a pair of gigantic laser interferometer, like spectrometer. You might have seen that actually, Michelson Morley experiment or maybe something like that. Any kind of a spectrometer you might have seen that for the estimation of the wavelength of the light or maybe the deviations. The LIGO project achieved was using pair of gigantic laser interferometers to measure the changes thousands of times smaller than an atomic nucleus as the gravitational wave passed by the Earth. So, for all sorts of electromagnetic radiation and particles, such as cosmic rays or neutrinos, have been used to explore the universe. However, gravitational waves are direct testimony to the disruptions in space-time itself. This is something completely new and different, opening up an unseen worlds. A wealth of discoveries awaits those who succeeded in capturing the waves and interpreting the messages. For that, they got the Nobels. In fact, this one picture showing that actually, see that this is the age of the universe, years, hours, seconds, milliseconds. At that time, they generate a wave frequency. It reaches here to a great extent. This is for terrestrial interferometers. This is for CMBR, and the sources are from binary supermassive black holes within this region, compact object captured by super black holes within the region, rotating neutron stars within milliseconds of that region. Being this is the gravitational wave from colliding black holes. See that about a 29 solar mass. One solar mass, you know that solar mass is the mass of a sun and its planets together. This is 36 solar mass. These two end spiraling, coming closer coming closer and hits. Both together becomes actually 30 plus 30, 30 plus 30, 65 solar mass, but some 5 solar mass, some 4, 3 solar mass has dropped due to the conversion. Solar masses of 62 became put together one actually. And Hanford LIGO, this made the observation actually. See, this is the waves, mechanical waves, sorry, this is the gravitational waves actually for these two. This is for the combined together. When it becomes one single one, the strength is quite large. The same description I have mentioned here. The two black holes which finally collide had moved encircling each other and produces a signal of great things what you expect. Yeah. This is the one what I shown earlier with the video. This is with the LIGO experiment. It looks like that. The emission was somewhere else far away. This is one mirror. This is a second mirror. You can see that the sun, earth, and moon here actually. And this is the experiment made on earth actually to a great extent from USA. And this signal transmitted about 1.3 light billion years away, and it took about 1.3 billion years to reach earth with a strength of the energy very less actually. How that these two mirrors are there, this I shown actually. Okay, if there are no disturbances, you can expect that the light travels equidistant about 4 kilometers away from each place. Okay, interferometer you get either constructive or maybe destructive depending on that with the intensity. Means if they recombine together, you'll get no signal at all, signal gets cancelled. But because of the gravitational wave detection, A and B are passing in such a way that, see, that is a strong signal you are expecting. The gravitational waves interfere these interferometers. These interferometers means these mirrors. These mirrors gets disturbed. Either they move apart, they move towards the detector. Because of that detector, because of this detection can be seen actually. See that the same thing with the two things, it is coming and coming. This is the LIGO experiment what they explained. In general, you can see that how to catch a gravitational wave. The words first captured gravitational wave here that this is a 4 kilometer apart. This is a signal generating and it interferes. I have shown with the enlarged image. You can go through it. Hardly I'm having another 5 minutes time actually. Yeah. Nobel Prize for detection of gravitational waves. Okay. There is the 1, 2, 3. These are the two mirrors 4 kilometers apart. Two laser beams travel perpendicular to each other from this post. This is a source actually. They interfere here at this point and can be detected with nullified. If the mirrors move apart due to the move apart or move inward or outward due to the generation of the gravitational waves that disturbs the electromagnetic radiation, particularly laser beam gets modified, you may not get the same signal as you expect. Detection of the gravitational waves makes it possible to work backwards to the first millisecond of the Big Bang theory. When Big Bang has happened, when the universe was created, how that universe was created within millisecond of the Big Bang. Albert Einstein predicted gravitational waves in 1916 in his general theory of relativity. That was evidenced by the three great scientists in 2015. Waves first detected on September 14, 2015. Origin is that fusion of the two black holes, which was happened 1.3 billion years ago. Thanks to this three group, sorry, uh, thanks these group of a group of scientists with the three of them, all of them from the LIGO and Virgo collaboration. Thanks to them. This is up to what I want to convey you on this. This is the last one. Thank you for joining with me right now. Happen. Are you able to listen to me?
Yes, sir.
Oh, somewhere I missed it. Okay. Okay, this is up to the class for me. If you want to ask any queries, I can attempt. Otherwise, I will share your video later. Thank you for participating today and for all the classes. These experiments are very good experiments actually, and you can learn to a great extent. If there are no queries, I can stop. Otherwise, we will see that what best we can do it. That's fine. I'll stop sharing. Stop.